So. All right, so I've highlighted the most important parts on each slide. Go ahead and show your computer so I can have your undivided attention. Remember, the internet's way cooler. I cannot compete with the internet. Okay, so the most important things I've highlighted here, some of this information you've embedded, like in individual parts, but if you want to add just a snippet of information about ZEF on the back of your folder or something, that's what this is. So we're just going to verify we understand what ZEF or nuclear effective charge really means. So it's talking about the positive attraction, or the force of attraction the nucleus has on electrons, and how if you have more protons, you have a greater force of attraction. If you have multi-electron atoms, meaning like anybody bigger than hydrogen, you also have to consider how electron repulsion comes into play, which doesn't necessarily affect the ZEF at all. It doesn't affect the nuclear effective charge, because that's just based on how many protons are in the nucleus. But if the electron repulsion comes into play, it reduces the nuclear charge felt by electrons, because it's simply blocking nuclear charge. So I'm going to let you finish reading what you need to read. Give me a thumbs up. I did not highlight this part, but maybe you know this, maybe you don't. The goal in all atoms' life is to become lower energy, which makes them more stable. Stability is key. So if you have a really high effective nuclear charge, or a lot of protons, that means that these energy levels that are close to you are more stable, because you're stabilizing them. The nucleus is stabilizing them by attracting them very strongly. So that stabilizes the inner energy levels, which pulls them a little bit closer to the nucleus. Because they come closer to the nucleus, they're more stable. And we're going to pass this. Okay, so the factor that we talk about across a period is ZEF, nuclear effective charge. The factor we talk about going down a group is what? Shielding effect. And we talk about, that's not this on the next slide. Going back to ZEF. We spoke of this when we talked about these radial graphs, how there's nuclear penetration of some orbitals versus others. The 1s orbital, the 2s orbital, the 3s orbital, basically all the s orbitals undergo a lot of nuclear penetration. Just simply means that the nucleus is super, super, super attracted to those sublevels, so they shrink in. So it's very, very, very difficult to grab electrons from those orbitals. So s sublevel electrons are usually going to be experiencing nuclear penetration. You good with that? Yeah.
How does the electron repulsion play in the kind of family?
Hold up, let me get there. I'm gonna make it to electron affinity. That's like in like 10 slides, Cassie. Hold up. Okay. So basically, if you're undergoing nuclear penetration, you have greater attraction, which will play a role in ionization energy here coming shortly. So the two trends or two factors that affect the trends is ZEF and then electron shielding. Right here. Electron shielding. So if we're ever trying to play into a factor, you're usually going to be mentioning one of those. And if you're not mentioning one of those, you're doing it wrong. Okay, that's basically what you have to say. Along with both of these comes Coulombic attraction. Because essentially, if you're closer to something that's positive and you're negative, Coulombic attraction is strong. If you're far away from something that's positive and negative, sorry, the distance is great, the Coulombic attraction is smaller or weaker. So you can always use that terminology. That's a kind of a win-win situation. If you're ever looking at like some variation across a period, and we're looking at ZEF, like you're looking at like sulfur and chlorine. Sulfur has how many protons? 16 protons, and chlorine has 17 protons. That's such a minor difference in the nuclear effective charge. It's not going to change the radius that much. It's not going to change the ionization energy that much. It's not going to change anything that much because it's only one proton difference. But if you're looking at some variation down a group, if you're going from like sulfur to selenium, and let's say you're looking at atomic radius, that's a huge difference because what have I done from sulfur to selenium? I add a whole nother shelf of electrons or a whole nother energy level. So that makes a really big difference in size, ionization energy, electron affinity, and so forth. So anytime you're looking for like where's the biggest variation, it's going to be down a group or up a group, not really across a period. Cool? So that might be an easy question to think about, like on a multiple choice. That's not important. Maybe graph, right? Okay. We know this is the ionic size. So if you're looking at cations, what happens when you form a cation? Okay, you're losing electrons, so you essentially lose the whole shell. Usually if you're like got one electron, if you lose the whole shell, you get smaller. If you only, let's say you're aluminum, you would lose one electron, you also get smaller. But why? Okay, so diminished electron or electron repulsion, and your proton to electron ratio goes up. Because if you lose an electron, you're down one electron. So your protons can actually pull on those remaining electrons very, very well, which the nuclear effective or the Coulombic attraction can be stronger, which is going to shrink the size of that ion. And then negative anions are going to be larger because we've done what to them? So we add an electron, what happens to their electron-electron repulsion? It increases, and the proton to electron ratio does what? Decreases, so the protons cannot effectively attract the additional electron, which makes that still kind of a larger ion. Give me a thumbs up when you're good here. Okay. Read that because I just explained this. Make sure you understand that. So again, nuclear penetration. The 1s and the 1s orbital is going to undergo more nuclear penetration than the 2p. So 2p sublevel is weak, less strongly or weakly attracted to the nucleus. So that's going to come into play when we start talking about taking electrons from 2p. Same thing for 2s. 2s electrons can undergo nuclear penetration, just lesser than the 1s because 1s is smaller. So closer to nucleus, more nuclear penetration. Can I go past here? Okay. So ionization energy. I just passed out a graph. We're going to look at that graph in just a second. Did everybody get one? Yeah. Okay. Good. So this is a lot, but you already have a lot of this down. So the key points here. Ionization energy is always referring to forming a cation. The equation that you should associate with that is, like, I'm going to say M for metal. So metal we're taking away an electron. So we're taking that away, removing an electron. But many times, to do any kind of work, we're going to have to put energy into this. So a lot of times these are going to, or actually, let's say always with an asterisk, because sometimes it's not, but they're usually always endothermic because to take an electron away, we have to put energy in because who's attracting that electron? The nucleus, right? So to overcome that attraction, we have to put energy in. So it's definitely endo. And we always talk about isolated gaseous atoms just because we don't work with molecules a lot in terms of singular electron removal. And when we're looking at ionization energy, they call them first ionization energy, second, third, fourth, and so forth. So you have as many ionization energies as you have electrons. So I mean, we could go to like 100th ionization energy. We would never do that because I'm not taking 100 electrons from, who's number 100? Who is it? DS. I forget, I don't even know the name of that right now. What is it? Oh, thanks, Faye. Very helpful. Okay. So you have as many ionization energies as you have electrons. We generally only work up to like maybe the 4th or 5th ionization energy number because that's as far as AP exam ever wants us to go. So what you should know are the successive IEs do get larger, and there's a reason why. As you take away electrons, right? So I'm just going to use that again. Let's do lithium. 3 protons, 1, 2. Okay, so it's got 3 electrons, right? When you take away the first one, that's going to require some amount of energy. But when you take away the first one, the full outside energy level's gone away. So now we're talking about taking the second one and then the third one. So what's now interesting about the second electron here? Okay, why is it harder to remove from lithium? So it's closer, right? So the Coulombic attraction to the nucleus is stronger, and there's less electron-electron repulsion, and you have nuclear penetration going on with the inside energy levels more so than the outside energy levels. So a lot of factors that play into this. So that's why the successive ionization energy gets higher and higher and higher, more endo, more endo, more endo, just because of the greater attraction or binding energy, as what we'll begin to call it. And then, so that's what this right here says. We good here? I have more to add to this, so wait 1 second, okay? All right, so you have this graph, yes? I noticed I zoomed in on the first. I try to zoom in on the first 8 electrons or 8 elements. So if you want to mark this for yourself, this would be helpful. Hydrogen is here. Okay, so label that hydrogen. And then helium is up here. So it was 1, 2. As you can see, it says atomic number on the bottom right. Okay, so who's after helium? Say again? Lithium. And then up here? Beryllium, Be, and then here? Boron. Okay, so let's stop there for a second. Generally, as we go across the periodic table, what is the general trend for ionization energy? From left to right? Increases because of increased what? Protons, or ZEP, or nuclear effective charge, or Coulombic attraction, however you want to say it. So hydrogen's low, helium is high. Boom, boom, done. Lithium is low, beryllium is higher. We're doing good so far, but then here's an exception. We would expect going across the periodic table that you just keep increasing because you have more protons. But why does boron have a lower ionization energy than beryllium? Anyone help me out there? It has something to do with Chase. Okay, so we're going to say 2p electrons, or the p subshell, right? So why does that matter? Right, because the s electrons or s orbitals are undergoing nuclear penetration. All right, so we have boron that's going to have a lower ionization energy because it's 2p subshell is farther away from the nucleus. It's of higher energy than the 2s electrons, plus the 2s electrons are undergoing nuclear penetration. Okay, I have this summarized down here at the bottom, but we're just talking about it first. So who's after boron? Carbon. Okay, so we expect the trend to continue, and it does. It's going up, so carbon has more protons, more ionization, or higher ionization energy. Who's after carbon? Nitrogen, and then next, oxygen. Okay, so oxygen disobeys the trend. It's an exception to the trend. Why would this be? Just give me some keywords here. Why is there electron repulsion going on in oxygen? Yep, you're right, orbitals. Okay, so basically there's an extra electron in one of the orbitals, right? So this is 2p, or 2s2, 2p3. So when we draw the orbitals, those 3p orbitals, how many electrons are in each one? 1, so there's very little electron repulsion. You take an electron out, that still requires energy, like endothermic still requires energy. So it requires less energy because oxygen is 2s2, 2p4. So it is, if I can do this in blue. So this is the 2p. Okay, I'm not drawing the 2s because it's way inside. So it goes 1, 1, 1, 2. So those are the 4 valence. There's 6, but there's 4 in the 2p orbitals. So taking away that electron right there is stabilizing. It's relief. There's a relief of electron repulsion. So does that require more or less energy to take away? Less. If it stabilizes the atom, it's better for the atom. It requires less energy to make that action happen. Okay, so that's the key points on all of these little zigzags. So from 2A to 3A, there's a drop because of what? Keywords here. So nuclear penetration versus taking p-level electrons. And then from 5A to 6A, there's a drop because you're taking electrons that are undergoing electron repulsion, and that requires less energy to do. Okay, And that's going to repeat itself, as you can see here, and there's over here, there's like 2 or 3 more. It's periodic, right? Periodic table. And yeah, here we go. So this is my big blurbs, but read and write down what you need to. We just spoke of it from the graph, but those are the most important points you need to set. I should say easier to remove, meaning less. So those are phrases or ways you can explain any Fourier-Trans question regarding ionization energy. All right, I'm going to go forward. Okay. So, yep, got that. Oh, no, hold on. Let's see if there's anything down here next to you. No, just another graph. Okay. And then the successive ones, we just spoke of this out loud, but basically your ionization energy is getting larger due to those ratios changing. That's what we kind of just spoke of. If you take away 1 electron, the proton-electron ratio is going to go up to essentially more protons relative to the electrons you originally had. So it strengthens that nuclear attraction. Stronger nuclear attraction means that's going to require more energy, more endothermic, for the next go-round, for that second ionization energy. And then again, as the cloud continues to decrease in size, because your protons are pulling in those electrons that are left, the third ionization energy is even greater. So what we should notice is a little bit of an increase. And then once we hit inner core electrons, so let's say I've been taking valence electrons this whole time, there's going to be a high ionization energy, like, I don't know, you could have 1,000 kilojoules it's requiring, 4,000 kilojoules, something like that. But as soon as you start to take inner core electrons, those electrons are much closer to the nucleus, right? So what would you imagine ionization energy would do? Like vastly increase. So it's going to be a huge increase. So it's going to be like 7,000 more, 7,000 kilojoules more, or 10,000 kilojoules more. So the way that looks, it's kind of fishy. Sometimes you're like, I'm not quite sure what a big jump is, but sodium, okay, first ionization energy, 500. Second ionization energy, 4,500. What happened? First ionization energy is taking what electron? The only valence, the single valence electron sodium has. The second ionization energy is taking its core, right? So sodium only has 1 valence electron. Once you take that one, you're in the core. That core is much more strongly attracted to the nucleus. There's a huge jump in ionization energy 1 to 2. But like magnesium, it's got a little bit of an increase, right? 700 to 1400. So that's taking its 2 what? Valence electrons, and then you jump to 7,000, right? Because what are we taking here? The core. So the third ionization of magnesium is huge. Aluminum goes, up. You think like 2,000 to 3,000-ish is a big jump, but relatively it's not a big jump according to the data. So there's 1, 2, 3 valence electrons, and then it jumps to 12,000. Big jump, right? So that's taking its core. So I can't say there's a right jump number, but if you look, it's a really, really big difference. So like silicon, you're going up to 4,000, and then it jumps to 16,000. So there is going to be a big jump. I just can't tell you how big the jump is because it kind of varies. We good with that? Okay, you try and tell me what is the electron configuration for this set of data. Basically tell me how many valence electrons does it have, and then tell me the electron configuration. So show me on your hands. How many valence electrons does it have? All right, see, I see 3s and 4s. Okay, so let's check this out. So we have a small amount of energy, a little bit bigger, but you're like, okay, that's kind of large, but let's check out the rest of the data. Okay, that's a little larger, and then you're like, holy cow, we're jumping to 12,000. Okay, so where have I started taking core electrons? E4. So this is inner core. This is supposed to be an I. Okay. Yeah. This is inner core over here. So these must be valence electrons. So how many valence electrons does it have? 3. So it might be something NS2 NP1. And those are the 3 valence electrons it's taking that are relatively easy compared to the rest. All right, read about that for a second. Okay, so ionization energy formed a what? Cation electron affinity is going to form an anion. So this is the wonky one. I hate it because it's endothermic and it's exothermic, which is going to skew like how we look at numbers. But to be honest, it's one of the lowly emphasized ones. So let's get a general understanding and move on. So if we're forming anions, okay, the electrons are going to be be attracted to the positive nucleus. Whenever an electron comes into an atom, let's say fluorine, and it's got 9 protons and 7. Okay, so it's got 7 valence electrons, right? When an electron comes in, fluorine's nucleus is attracting that electron to some extent. Everybody's electrons are going to be attracted by the nucleus, but at some extent. But this is a special circumstance because once it hits in here, it now has octet, which makes it more stable. So if there's any stabilization of the atom, it's going to be a very large exothermic value because when an atom is stable, it releases its extra energy, which is another way it makes it more stable. So the halogens are all going to be negative in their electron affinity value. Who else is going to be negative? Who else is stabilized by incoming electrons? Say again? We get group 7 for sure. Group 6, kind of. Group 5, absolutely not. Because group 5 has how many, what's its electron configuration? So that's like, S2, 1, 2. Let's put in there. And then whatever NP3. So that's its electron configuration. So if you throw another electron in there, what are you causing? More electron repulsion. So you're causing some disastrous disruption to its stability. Because this is actually as stable as it's going to be right now because it's got all those electrons separated somewhere apart. But if you put an extra electron in here, you're causing more electron repulsion. So that becomes less exothermic and more endothermic because you're actually making it have more like anxiety, less stability. That's going to require energy to do that. So tell me another one that would not really be willing to accept extra electrons. Another group. Group 2, right. Beryllium's group already has a full S level, so when you add an extra electron, you're adding it to the P's, which gives, you may not remember this, but S electrons are a little lower in energy than P electrons. This is like the all-fall diagram of energy. So if you have a full shell of S, you're close to the nucleus, you're stable. If you add extra electron here, you have more energy, which makes you less stable. So it does not want to do that. Therefore, it's going to have an endothermic or like a 0 value for its electron affinity because it's not exothermic. It's not stabilizing. You see how this one's a little crazy? It's just weird. So here's the graph for this one. Hydrogen has, why does hydrogen have a negative, no, this is positive. Why does it have a positive value? This graph, hold on, this graph might be flipped. This is beryllium. This is supposed to be negative up here. I pulled another graph because I didn't like the graph I had. This should be positive. Yeah, okay. So looking at this graph, why is hydrogen exothermic in its electron affinity? Okay, so when you add, it's only got one S electron, right? So when you put another one in there, it becomes a duet, right? So hydrogen can achieve up to duet, not octet, because it's just so teeny tiny. So that's almost like its noble gas electron configuration. Lithium does not really become more stable, but it can accept an extra electron, and it's stabilizing in such a way because it's got a small atom, and its nucleus is really close to the outside, so it's going to be stabilizing by accepting or attracting that electron. Beryllium here is in the positive region, like we said, because of electron-electron repulsion, and for this one, 2p electrons being added. And then group 5, nitrogen, we see how it's on the 0. It doesn't really want extra electrons. It will take it, but it doesn't necessarily want them because, like we said on the board over here, taking on that extra electron gives you more electron-electron repulsion, leaving you less stable. But fluorine's like, heck yeah, let me release some energy, right? Because it does want the extra electron. Even with the extra electron, like fluorine would be, before accepting an electron, it would be like this, right? Right, 7 valence electrons. So when we add an extra electron, we're truly creating what? Okay, so we're creating a good noble gas electron configuration, but we're creating electron repulsion at first, right? One would think that's not desirable. But the 9 protons are going to effectively attract that extra electron, and it creates a stable electron configuration. So it's more exothermic than endothermic. Therefore, in the end, we claim it as exothermic, meaning stable. Okay, we're going to get past this one. It's not my favorite, but 2A and 5A are where the exceptions exist. Yeah. Whole shells are more stable. We say that because of minimized additional electron-electron repulsion, but we never would say, like on the AP exam, full shells are stable or half shells are stable. We would talk about the electron-electron repulsion or talk about the proton-to-electron ratios to justify all of our answers. There's some things we can think, but we can't say. Does that make sense? Because we can think it to help us like get the idea, we just can't say them because they're not truly the justification needed. And then my final comment is electron affinity is weird. Okay. And then this is what we just explained. I'm going to pass this. Electronegativity should be our last one for now. And this one doesn't really have any exceptions. There might be a little bit of a wiggle throughout, like not a definite linearity, but there are not really truly any exceptions. What we know is that as electrons, or as we go across the periodic table, across a period, what is changing? What factor? The ZEF, or the nuclear effective charge, or the Coulombic attraction, is stronger. So, as you're talking about electronegativity, you're not talking about truly gaining a full electron. You're sharing an electron in a covalent bond. Bonding is our next unit, and this will be like our VIP on the next unit, but we're just going to minimally hit it for today. So, this is really big in bonding. And if you don't remember what a covalent bond is, it's when two atoms share some internuclear space. So they put their electrons in the internuclear space, and they can kind of both act like they have a hold on those electrons. So if I have an atom and a bond and an atom, there are 2 electrons in this bond. If I have a double bond, how many electrons are there? 4. If I have a triple bond, how many electrons are there? 6. So regardless, there's nuclei, right, positive nucleus, that are attracting these electrons. But if you have more ZEF, or nuclear effective charge, what are you going to do to those electrons?
Well, just to one side.
They're just going to scooch to one side or the other. They're not going to be totally exchanged. It's not ionic bonding, it's covalent. So let's say these 2 electrons are going to be pulled this way. Maybe this is fluorine and this is carbon. Carbon has lower ZEF, fluorine has bigger or larger ZEF. Therefore, it's going to pull the electrons one way, simply because it's got more protons. And then we can call out the term electropositive, but we never will. It's just something to let you know there are substances that are electropositive, but that's because they have really low electronegativities. So who's not going to be forming covalent bonds? Period. Metals, right? So they don't really have a high electronegativity whatsoever, which is why we have this thing going on a group. In group 1, who is most electronegative? Group 1. Lithium is more electronegative than like francium, but that's because it has less electron shells or less electron shielding. Yeah. That's going to be my next point. So I don't call it an exception necessarily, I just call it a nuance, because in terms of electronegativity, since we're talking about bonding, do noble gases bond? Generally, they do not. There are some though. So this graph, yeah, this one actually shows it. So I'll show that over here. If you look here, there's no data for helium, neon, and argon, because these are not going to bond. They're not going to share electrons. So they have zero, like a zero for their, or actually have no data for their electronegativity. But xenon, nope, that was krypton. Xenon and krypton, that's Kr, okay, they actually can bond. So what we'll find is like xenon tetrafluoride, it can bond because it truly has so big of orbitals, they can tuck in extra electrons and sharing, no problem. Xenon can do the same thing. So we show data points for those. It's just there's a nuance here because these are teeny tiny and they're not going to share electrons. Okay. And then we don't really talk about transition metals. Can I go past this? And then within melting point and boiling point, this will make a difference. Some ideas about how electrons are loosely held or not so loosely held. But someplace on your booklet or foldable, add something about metallic character and non-metallic character, which are these 2 points here. Metallic character and non-metallic character. This eventually will play into melting point. Eventually. So if you want to put it on there, that's fine. This also plays in the bonding, why ions form, and everything. So metallic character or metallic nature means to to lose electrons. It's simply because the electrons are loosely held or they have a low what? Okay, so low Zeph, so sorry, give me some trends. What are some trends that follow along with metallic character? Okay, so I'll say, tell me how the atomic radius looks. Okay, so a high atomic radius means that you're going to have higher metallic character because your electrons are so far away from your nucleus, you have no care in the world, those electrons leave at will. Tell me about ionization energy. High or low? Low ionization energy because you don't require a lot of energy to swipe that electron away. So who's the most metallic of the alkali metals? Say again? Francium, because it has low IE, it has a large atomic radius, it has low electron affinity. It's like, nope, don't want the electron at all, and it's got a low electronegativity. Okay, so the most reactive of everybody in group 1 is francium because it has the most metallic character. It's the most willing to react, the most willing to give up electrons of them all. Do you see how that relates to reactivity? Reactivity just means like, will exchange electrons. Non-metallic character, those are going to be the ones that are what in terms of atomic radius? Smallest, meaning that they are so small, their nucleus is so close to the perimeter, bye Margaret, so close to the perimeter, they will take on the extra electron and continue with that electron again. No, this is so fun. I'm learning the learning. Just tell me now. So anyway, the rest of these, high IE, they want electrons, high EN, they want electrons, and high EA, they want electrons. Okay. Who's the most reactive of the nonmetals? Fluorine, yes. This one. I was not paying attention on that here. Thank you. All right, questions here so far? There we go, Megan. Thank you. All right. Can I go past this? Metallic means to lose electrons, and non-metallic means to gain electrons. And, yep, we're going to move on. All right. And then this is just a nice conclusion to the general trends. Of course, there are exceptions. Good. Metallic character increases down to the left. It follows the same trend as who? Atomic radius. Non-metallic character increases up and to the right, which follows the same trend as everything else. Okay. Let's do this later, okay? So just I'm going to fly through a couple things I'm not doing just yet. Okay. Pull out your packet under trends. I think it's on page 3. Now, I do want you to finish your little booklet so I can award a project grade, so ensure that it's done. Let's see, today's Wednesday, by Friday. Right? That gives you enough time if you need to embellish it some with more facts or pictures or blood, sweat, and tears, whatever. Okay. So this shouldn't take us very long. E through J, so 1E through J. You guys see where it says periodic trends? I want to say it's not called composite, but it is composite. Yeah, it just says AP Chemistry periodic trends. It's on page 7. See where I put like a 7? I'm trying to get better. Okay. So E through J, 2, 4, 6, 7, 9 through 11, 15, 17. Okay? Start with those, and I'd like to check those before we go. Let's see where we are in like 10 or 15 minutes. Of course, use a friend and use a book. Use me. All right, guys, come back to me where you can. All right, so we're going to try to chant this out loud so I don't have to call on you. Ready? 1E. Sodium, not sodium plus, right? Larger radius is what happens to sodium plus? It gets smaller, right? Your cation, you lose a shell basically, or you lose some gaining or some advantage you have over the nucleus. So sodium itself is larger. F, S2 minus, because you got two extra electrons due to repulsion. So if you want to add on this little bit of like commentary, that might help you remember why you chose that, right? So S2 minus is 2 extra electrons for that's causing repulsion. Okay. G. Calcium is larger because it has extra shell. Okay. H. Bromine's bigger because it has 2 extra shells. Okay. I. I heard calcium 2 plus, and I heard chlorine minus. So I'm gonna show you on the periodic table. Okay. So calcium, when it loses its 2 electrons, it looks like the noble gas electron configuration of argon, right? So it bounces back to only have a total of how many energy levels? 3, right? Okay. But chlorine also has 3 energy levels, right? But calcium has 2 less electrons. So who's winning here on this battle? Well, no, in the proton versus electron ratio. Protons are really pulling in the extra electrons left over from calcium. So calcium's not only small because it lost its 4th energy level, it's even smaller because it's got more protons to electrons ratio. Chlorine is larger than calcium 2 plus, because chlorine is it's got 3 energy levels, but then you add an extra electron in there. So what's the electron doing? The electron-electron repulsion. So it blows up that 3 energy level cloud just a little bit bigger. So chlorine 1 minus is larger than calcium 2 plus. J? S2 minus, right? S2 minus has 2 extra electrons, which means the first one gets it like if you had S1 minus, it might be as large as chlorine. As you can see, it's 1 different here. But the second electron makes it even bigger due to electron-electron repulsion. Yeah. Most of the time, unless there's a vast difference in energy levels, because the energy level is going to be a big change versus that little bit of electron-electron repulsion. All right, 2. A. Bromine, because it has more protons. F, right? B. Chlorine, because it has less shielding or energy levels, right? Okay. I would say shielding if I were you. That's a better term. C. Oh man, is this an exception to the trend?
Today.
So why is magnesium higher in ionization energy? Don't say because it has complete shell. There's a better reason. The weird word I have to keep saying out loud. Nuclear penetration, right? S block undergoes nuclear penetration. Aluminum's in its last electrons in the 3p. 3p does not undergo nuclear penetration. So magnesium has a stronger or higher ionization energy due to nuclear penetration, or S block penetration, as you could say. D. Who? So nitrogen. I know they're on different energy levels essentially. Nitrogen's pretty high, but why potentially could sodium plus have a higher ionization energy? So its ratio is that of neon, right? It's proton to electron ratio, and you're plus charge. Are you going to take another electron from sodium? Have you ever seen sodium 2 plus? Never in your life, right? So that is going to have it's a cation, so it's got a positive charge. Proton-electron ratio is skewed. It makes it even harder to achieve another electron off of it. So, plus, if I take another electron from that, what am I stealing from it? It's core electrons. That's going to jump up a good 12,000, right? It's going to be very, very, very difficult to take that. So sometimes, think about the trend, but then think about what's really happening. I think you can do it. Okay, keep going. Let's go. I'm going to go down to multiple choice for a second, as many of you did. 6. A, good. Less protons makes it big, or less protons makes calcium bigger. 7. A, and that's what, beryllium? Or BE? Yeah, beryllium. Why is the third ionization energy biggest for beryllium? Has 2 valence electrons, so the third energy, or third IE, would be taking its core. Okay, that's good. That's an easy question to get right, since you guys know how to think about that now. 8, I didn't have you do the boiling point. 9. Just wait. 9. A. Okay, so oxygen. Why is oxygen the lowest? Less protons, and it's also an exception, right? Because oxygen has the fourth electron in p block, so it's even lower than what we actually think it is. 10. A. Okay, so periodic is nuclear or is F, and then 11. B is shielding, so remember that your 2 key words or 2 key factors. Let's go down to 15. Who is the greater IE? Why nitrogen? Because phosphorus, nitrogen and phosphorus, right? Okay, so what's the big difference here? Shielding effect. So lesser shielding effect for nitrogen. Yeah. And then, so I need to, let's do the rest of these, yeah. B. Why magnesium? Higher Zeth. And then C. Hydrogen Qui, because?
It's shells. It's energy, it's subtle shells going through nuclear penetration, and it's what it puts it in the nucleus. Okay,
so it's got 1 energy level, the S block. S block's undergoing nuclear penetration. Hell no, you're not taking that electron, right? Bromine is really, pseudo far away. It's 4 energy levels. You could totally take that electron, no problem. Even though it doesn't want you to, it's much easier to take bromine's electron than hydrogen's. And then 17, based on your knowledge, which halogen is will most easily gain electrons? A. Why fluorine, Drew? Okay, less shielding. It's got a high Zeth of all of them, but less shielding is the best way to elaborate. B, which halogen most easily loses electrons? Iodine. Acetine is actually a halogen. It's just not a common one, but I or AT would work there. And it's because it has, say again, more shielding, right? And then do halogens prefer to lose or gain? Gain. And then given your answers, how does reactivity play into this for fluorine versus iodine? So does it increase in reactivity from fluorine to iodine, or does it decrease in reactivity from fluorine to iodine? Decreases in reactivity. So reactivity can come in two forms. Reactivity means the ability to exchange electrons. Nonmetals are going to do what with their electrons? Nonmetals are going to what? Gain electrons. So fluorine's more willing to gain electrons because it's got less shielding. Iodine is less willing to gain electrons, but it still wants to because that's more shield. It's all about the shielding on that row right there. Okay. All right. So hold on one second because I know we're getting ready to leave. Did you guys find those two FRQs? 82 and 87. They're way back. What page are they on the inland scribbles? No scribble. The next page? Never mind. I'm thinking about something else then. Yeah. So 82 and 87, I'd like to check tomorrow. So, take some time. Use your brain. I know you guys can check yourselves and you have that, need to check yourself immediately. So just let's check them tomorrow. You're fine. Okay? So we finished our thumbs up. Yay! Shut. And then your two FRQs. Okay? And at some point in time, put that Bohr lab in the box so I can get that credit, so I can help your average that plummeted after I put midterm grade in. Notice how many times I put that midterm grade in. How many times did I put it in? Once. I have a big heart. I know this class is